Okay, some of the last stuff that we have to do here with derivatives is just making connections between our graphs, the derivative, and we're going to talk a lot more about the second derivative that we haven't done so far. So it says, let's begin by remembering what we learned about connections between a function f and its first derivative f prime of x in the context of functions. So now that we know how to take the derivative of all type of functions, we have to tweak our understanding of this concept. Oh, wait, what was the concept? Well, remember that we talked about when a derivative equals 0, it has a horizontal asymptote, and when it is positive, it's increasing, right? So we just want to kind of connect these. So notice this is a polynomial function. It's a smooth curve, no sharp corners, nothing crazy happening. And so it says at what values of this of x does g of x have a relative maximum or a relative minimum? Remember, that's going to occur at the turning points, right? At where the turning points of the graph. So we can just look at this, hopefully, and know that x equals 0 is a relative max, and at x equals 2, it's a relative min. And it says, what can be said about g prime of x at the values indicated above? Well, what do we know about the derivative when there's a relative max or min? Well, hopefully, we remember that that means the derivative equals 0, which means that it has a horizontal tangent line, right? Like you could draw in a horizontal tangent line on those graphs, right? And then at the bottom here it says, oh, that's f prime of x. Okay, so then compare that to this one. At what values of f of x does f of x have a relative max and a relative min? Well, on this one it doesn't have a relative max, but at this point right here, looking at the graph, you can definitely see that that's a relative min at x equals -1. But what do you know about the derivative here of f prime of x? It's undefined at x equals -1 because there's a cusp or a corner in that graph, right? And so when we deal with polynomial functions, it's really easy to find max and mins, but it says we have to think about our definition now. So look, let me just kind of show you this, and then we'll get to our new definition. It says algebraically find the derivative of f of x, and then perform a sign analysis to show where it's equal 0 or undefined, and then we can show this up there. So our derivative was f of x equals x plus 1 to the 2/3 plus 2. If I was going to take the derivative of this, right, that's just the chain rule where I would say 2/3 times x plus 1 to the -1/3. The derivative of the inside of that's just 1, and then the derivative of 2 is 0. So you could write that as 2 over 3 times the cube root of x plus 1. So if I asked you where does that equal 0, it doesn't ever equal 0. Where does f prime of x equal 0? The top's never going to equal 0. But where is it undefined? It's going to be when x equals -1, because remember, undefined would be where it's in the denominator. And so if we add this addition, that relative max or mins can occur not only where the derivative equals 0, but also where it's undefined, then we're going to be able to do this with all functions. So remember when we did this before with the sign analysis? It's been a while. But I would take and I would plug in values into my derivative on either side of this to see what's happening. And if I plug -2 into this, I'm going to get a negative number. And if I plug 0 into this, I'm just going to get 2/3, which is a positive number, which we can see that it's changing from decreasing to increasing there, even though it's a sharp corner. So it is a relative minimum at x equals -1 because f prime of x changes from negative to positive, right? So as we've learned about all these other functions now, we have to expand our definition. So it says polynomial functions deal with critical numbers where the first derivative is equal to 0. Since that initial investigation, we've talked about places where a function is not differentiable. In other words, where places have a cusp, but that doesn't mean it can't have a max or min at a cusp or a corner, right? So this is a word here, a definition, critical numbers, is a value of x where a function's derivative is equal to 0 or is undefined. Basically, it's where possible max or mins can happen, right? Like it's like potential relative max or mins. So let's just remind ourselves of this. This should be memories that we have. If we know the derivative of x is equal to 0 or undefined at a specific value, then f of x has a possible relative max or min at x equals a. What do we know if the derivative is greater than 0? Well, we know that f of x is increasing. If the derivative is less than 0, we know that f of x is decreasing. And very specifically, not just if it equals 0 is undefined, but if it changes from positive to negative at a point, then we know that f of x has a relative maximum, positive to negative. And if it changes from negative to positive, we know it has a relative minimum, negative to positive. Okay? And so we've done all of that. We just haven't talked about it being at undefined parts. And so it says the first derivative of a function identifies intervals where a function is increasing, decreasing, has a relative max or min. That's not new to us. New to us that we've only talked about in terms of tangent lines over approximating and under approximating is the second derivative identifies where a function is concave up, concave down, or has a point of inflection. A point of inflection is where your graph changes concavity, okay? It says in pre-calculus we said you could find approximate points of inflection if you knew the coordinates of the relative max and mins. State the intervals where the graph is concave up and concave down. And so basically it's like halfway between the max and mins is how you kind of think about it. So if you think about this, tangent lines are above graphs that are concave down and below graphs that are concave up. And so you know this is a relative max and this is a relative min. So where does this graph change concavity? Roughly about halfway in between there, that we could say this side of the graph is concave down. This would be concave down, which means your tangent lines are all above that line. And then this side, we call this concave up. So we're going to work with the second derivative a little bit more in this chapter. So let's see if I can get through this slide. Maybe. At least part of it. So it says find f double prime and perform a sign analysis. And what does this tell me about the second derivative? And so the second derivative is when we can look at concavity. And so the equation for g of x on the previous page was x cubed minus 3x squared. So g of x is x cubed minus 3x squared. And so if I do the first derivative, that would be 3x squared minus 6x. If I do the second derivative, I just take the derivative again, and that would be 6x minus 6. So just like I did with the first derivative to find max and mins, I'm going to do this with the second derivative. So I'm going to set the second derivative equal to 0. So 6x minus 6 equals 0. And I hope you agree with me that you get x equals 1. Just like we did with the first derivative, I can do the little sign chart here and put 1. But now I want to know what's happening with the second derivative. So I'm going to plug numbers in on either side of my second derivative and plug it in right here. And if I plug 0 in here, I'm going to get a negative number. And if I plug 2 in here, 12 minus 6, I'm going to get a positive number. What does that tell me? Second derivative tells me about concavity. So this tells me that my graph is concave down on the left side of 1 and concave up on the right side of 1. If you go back and look at that picture, you can see that I guessed that to be at 1. It's like halfway in between your max and your mins, is what we call an inflection point. Okay? I went the wrong way. So we can say, because it changed, that x equals 1 is an inflection point of your graph. Okay? So if I set my second derivative equal to 0 or undefined, these are possible inflection points. I like to call them PIPs, possible inflection points. What do I know about my graph if my second derivative is positive? I know my graph is concave up. What do I know if my second derivative is negative? I know my graph is concave down. And if my second derivative changes from positive to negative or negative to positive, both of them are just a point of inflection. It doesn't really matter which one it is, right? So you don't have to check as closely like a max or a min. So either one of these, then f of x has a point of inflection. Because the sign changes. Okay? Let's see where my time is. Too long. 11 minutes. Okay. So for each of these, I want you to take, determine the points of inflection. So see if you can take f prime of x and f double prime of x and set it equal to 0. This is a product rule here. So let's see where we can get on that. And then we'll start here in class.